The concept of scalar field is comparatively easy, but the concept of vector fields may require a bit more practice in order to get familiar to it. Generally speaking, a vector field is a function that goes from r to the n into r to the n. We write such a function as follows. F goes from r to the n into r to the n. That is a vector field. And what it does is takes a vector and maps it to another vector with coordinates f1 of x and so on up to fn of x. Each coordinate is a function that itself will depend on x. So in some sense you've got several functions that depend each on x stacked up into a vector. f1 up to fn. It will be helpful to have a look at a few examples. The first example will be a vector field in two-dimensional space. We have a vector field f going from r to the 2 into r to the 2. And what it does is it takes a vector with coordinates x1 and x2, and these are mapped to negative x2, x1. In this case, each of the two coordinates in the output vector depends on x1 and x2. In fact, the first coordinate is just negative x2. It only depends on x2 in this case. And the second coordinate is x1. It only depends on x1. The second example is a three-dimensional vector field. Let's call it G. It maps from 3D, three-dimensional space, r to the 3 into r to the 3. And it takes a vector x1, x2, x3 and produces out of that the following three-dimensional vector with the following coordinates: 2x1, x2 plus x3, and x1, x2, x3. In this example, f1 is just 2x1, f2 is just x2 plus x3, and finally f3 is just the product of x1, x2 and x3. Vector fields are present all over the place in science and engineering. They've got tons of applications, tons of physical concepts are modeled in terms of vector fields. So some applications that I would like to point out here. Generally speaking, vector fields describe the flow of something. There's one huge application, for example, in fluid dynamics. The motion of fluids is modeled in terms of vector fields. They may describe velocity. Depending on the physical application, they may describe acceleration. And for example, in physics, they will describe force fields. Every good physicist knows that drawing pictures is extremely helpful in understanding mathematical concepts. So let's do the same thing with drawing vector fields. Let's have a look at the vector field f from the previous slide. So we've got f going from r to the 2 into r to the 2, mapping x1 and x2, to negative x2, x1. The very first thing we do is we draw our coordinate system. We got x1 and x2, the x1 axis and the x2 axis. And let's see what are the values of that vector field at a few selected coordinates. Let's say here we've got the point 1, 0. The vector being produced by this vector field will be the vector 0, 1. And we illustrate that as follows. We take the vector 0, 1 and plant it at this position, 1, 0. Let's have a look at another position. Let's say down here we got the position negative 1, negative 1. If you now compute the vector field at this point, well, the vector field will produce the vector 1, negative 1. And that will correspond to the vector pointing in this direction here. Maybe another interesting coordinate is just 0, 1. And the vector field will produce the vector in direction negative 1, 0. In fact, you can continue this example with a few other positions. And generally speaking, the vector field that will emerge will look like a circular flow. And the further you get away from the origin, the faster the flow will look like. So the physical interpretation of this vector field will be a circular flow around the origin. And the further you get away from the origin, the stronger the flow becomes. In fact, this very simple vector field is very important, and it will help us to illustrate a few concepts later on when we discuss the divergence or the rotation operator.